In a world increasingly driven by technology, the infrared sensor, or IR sensor, emerges as a pivotal component in numerous applications. This video embarks on an exploratory journey into the essence of IR sensors. It unravels their fundamental nature and their critical role in modern technological advancements. IR sensors have become indispensable to our technological landscape, from simplifying everyday tasks to enabling complex machinery. As we delve into their intricacies, we discover how they function and shape the interaction between technology and our daily lives. Check our other videos. IR sensor working is explained in simple terms in our site and YouTube. The IR LED and the photodiode are at the heart of an IR sensor's functionality. The IR LED emits infrared light, which gets reflected upon hitting an object and is detected by the photodiode. This simple yet effective mechanism enables an IR sensor to perform its task. Discover everything about the IR sensor module, Infrared Sensor Complete Guide. Learn more in our YouTube for easy, comprehensive insights. However, not all IR sensors are created equal. There are two main types, active and passive IR sensors. Active IR sensors are the more interactive ones. They emit infrared light and detect its reflection, making them perfect for applications requiring direct measurement. On the other hand, passive IR sensors are often used in security systems. They work by detecting the infrared radiation emitted by warm objects like human bodies. Active IR sensors create and detect signals. In contrast, passive IR sensors quietly observe and pick up infrared energy. This difference leads to diverse applications. Active IR sensors excel in targeted detection, while passive IR sensors are preferred for surveillance and motion detection. Active IR sensors are the cornerstone of precision in the sensor technology landscape. These sensors operate by emitting a beam of infrared light, which reflects off objects and returns to the sensor. This mechanism allows for exceptionally accurate object detection, making them indispensable in applications requiring high precision. For instance, active IR sensors reliably detect and count products in automated manufacturing lines, ensuring efficiency and accuracy. Moreover, in consumer electronics, they enhance user experience by enabling remote control of devices like TVs and air conditioners. Their ability to measure distances makes them invaluable in robotics, aiding navigation and obstacle avoidance. Passive IR sensors, a marvel in sensor technology, stand out for their ability to detect natural infrared radiation emitted by objects. Unlike their active counterparts, these sensors do not emit any infrared light. Instead, they are finely tuned to sense the subtle infrared energy naturally given off, especially by warm objects like the human body. This unique capability makes them incredibly useful in various applications. For instance, in home security systems, passive IR sensors provide a reliable and non-intrusive way to detect potential intruders by sensing body heat. Furthermore, they find extensive use in energy-saving applications like automated lighting systems. Lights activate upon detecting the human presence, favoring passive IR sensors in residential and commercial settings. This non-invasive tech improves safety, convenience, and energy conservation, harmonizing functionality with eco-friendliness. IR sensors can detect the presence of humans in many ways, including motion detection. IR sensors can detect the presence of a moving human by measuring the amount of infrared radiation emitted by the person and the surrounding environment. When a person moves, the sensor detects a change in infrared radiation, indicating their presence. Furthermore, this change is directly linked to the person's movement. Proximity sensing. IR sensors can detect the presence of a person close to the sensor, which is particularly useful in applications like automatic doors and automated lighting. Temperature measurement. IR sensors can measure a person's or any other object's temperature by detecting the amount of infrared radiation they emit. This capability is functional in applications like fever screening and industrial process control. Other applications. IR sensors are also used in a wide range of applications that may involve the detection of humans, such as security systems and automotive collision avoidance systems. Although IR sensors can detect humans, other sensors, such as cameras and radar, may be more accurate and reliable for human detection and tracking. The distance range of an infrared IR sensor depends on many factors. Some factors that can affect the distance range of an IR sensor module include type of sensor. Different types of IR sensors have different distance ranges. For example, proximity sensors, which detect the presence of objects close to the sensor, typically cover a distance range from a few centimeters to a few meters. Motion sensors, which detect the movement of things, can cover a distance range of several meters or more. Sensitivity of the detector. The sensitivity of the detector in the sensor plays a significant role in determining its distance range. Sensors with more sensitive detectors can detect objects at greater distances. Strength of the emitted radiation. The power of the emitted radiation also affects the sensor's distance range. Sensors that emit stronger radiation can detect objects at greater distances. Significantly, the distance range of an IR sensor module can be expanded by utilizing a lens or other optics to focus the emitted radiation into a narrow beam. This approach offers distinct benefits, particularly in situations requiring object detection at extended distances. Pulsed IR sensors. These sensors, a subtype of active IR sensors, emit short bursts of infrared radiation and measure the time it takes for the reflected radiation to return to the sensor. Pulsed IR sensors find widespread use in applications such as range finding and velocity measurement. Continuous wave IR sensors. These sensors, also a subtype of active IR sensors, emit a constant beam of infrared radiation and measure the frequency shift of the reflected radiation. Continuous wave IR sensors are commonly used in distance and velocity measurement applications. Modulated IR sensors. These sensors, another subtype of active IR sensors, employ intricate modulation schemes. They excel in their functionality by encoding information in the emitted radiation and measuring the phase shift of the reflected radiation. Consequently, modulated IR sensors are commonly employed for proximity sensing and distance measurement tasks. The selection of an IR sensor depends on its type and intended use. Necessary specifications to consider include: detection range. The detection range of an IR sensor, measured in units like centimeters or meters, determines its maximum distance for object detection or temperature measurement. Field of view. FOV. An IR sensor's field of view represents the detectable or measurable area, typically specified in degrees or other angular units. Sensitivity. An IR sensor's sensitivity, determined by its ability to detect minor differences in infrared radiation, can be specified in terms of the minimum detectable temperature difference or power level. Accuracy. An IR sensor's accuracy is quantified by its level of precision and reliability. Specifically, this is determined by the deviation between the measured and actual values. This deviation can be expressed either as the maximum allowable error or as the measurement uncertainty. Response time. The response time of an IR sensor, indicating how quickly it detects changes in measured infrared radiation, can be specified in units like milliseconds. It characterizes the sensor's speed in capturing fluctuations in infrared signals. Operating temperature range. An IR sensor's operating temperature range defines the temperatures it can accurately function within. It is specified in degrees Celsius or Fahrenheit, providing crucial guidelines for optimal sensor performance. Operating wavelength. The operating wavelength of an IR sensor determines its sensitivity to various segments of the infrared spectrum. It signifies the range of infrared radiation wavelengths to which the sensor is responsive, typically specified in nanometers or other wavelength units. Depending on the specific application, other specifications may also be relevant for an IR sensor. Therefore, when choosing an IR sensor, it is crucial to carefully consider the required specifications to ensure its suitability for the intended use. Compared to thermal IR sensors, quantum sensors detect photons and are much more sensitive than sensing heat. Quantum infrared sensors represent the cutting edge of IR sensor technology. They are wavelength dependent and known for their quick response times and high detection accuracy. They require periodic cooling to ensure precise measurements, making their operation slightly more complex than thermal sensors. Quantum infrared sensors find their use in highly specialized applications, such as spectroscopy, where they help identify different materials based on their infrared signatures. Astronomers also use them to detect celestial objects not visible in the regular light spectrum. Only detecting objects in the 3 to 20 micrometers IR range, quantum well IR sensors are limited to mid-IR and far IR bands. Compared to thermal IR sensors, quantum sensors detect photons and are much more sensitive. The signal output of a quantum detector, typically a gallium arsenide (GaAs) semiconductor chip, is very small and easily swamped by noise generated internally to the sensing device at room temperatures. To overcome this problem, quantum sensors are often operated at cryogenic temperatures such as 77 K liquid nitrogen or 4 K liquid helium to minimize the noise. This significantly increases their cost. Consequently, they are only used if high sensitivity, high resolution, and/or short response times are required at a specific wavelength. For really far imaging, NASA's Thermal Infrared Sensor, TIRS, on the Landsat 8 satellite measures land surface temperatures using quantum well infrared photodetectors, QWIPs, to detect long wavelengths of light emitted by the Earth. This quantum IR sensing employs GaAs semiconductor chips that trap electrons in an energy well until the electrons are elevated sufficiently to a higher state by thermal infrared light of a certain wavelength. The measurements help track how land and water are being used on Earth. There are dozens of distance sensors on the market, and as they become more ubiquitous in electronic devices, they continue to get smaller, cheaper, more sophisticated, and more power efficient. The principles laid out here should give you a basis for assessing new sensors as needed.